In this video, we'll be talking about discontinuities, specifically discontinuities of rational functions. So in this case, a jump discontinuity doesn't actually occur when we talk about rational functions. A jump discontinuity specifically only occurs when we're looking at functions that are piecewise. So again, when you're drawing a piecewise function, say you might have a quadratic here that comes to about here, ends with an open circle, and then maybe a linear function that comes after that. This right here would be considered a jump discontinuity. Again, there's no point that's going to be consistently identifying from one line to the next. You have to actually, when drawing these two lines, move your pen up to another location and then continue drawing. Again, this is a separation in the values of y. That jump discontinuity can appear again in terms of being slightly different, where the domain, the range values are all accounted for. For instance, there's a hole in the range values here, but you can have that linear function down here and move up this way, and it still be considered jump discontinuity. Now, a hole discontinuity can appear in a rational function. The hole discontinuity does seem as though you're going to have to pick up your pencil, but logically it's just there's a single point in the graph that doesn't actually exist. So if I draw an open circle there, and I draw another linear function that passes through that open circle, such like this, that is a hole discontinuity. There is an entire function of values here where there's one spot, just one point in the entire function that doesn't actually exist there. The third type of discontinuity is a vertical asymptote. Now, an asymptote is specifically, again, a imaginary line that guides the function in some specific way. In most cases, rational functions have both vertical asymptotes and horizontal asymptotes, but please make note that a vertical asymptote is a discontinuity, while a horizontal asymptote is not. So in this case, vertical asymptote, again, would appear as though a graph of a dotted line. If you're looking at a graphing calculator, it won't necessarily show you this. If you're looking at an older version of a graphing calculator, what it'll look like a solid straight line going vertically up and down. For these particular graphs, you should be drawing the dotted line in there at the location where that vertical asymptote happens to appear. In this case, I might say that the hole is at x equals 0. In this case, I might say that the jump is at, say, -1. And then for this one here, I might say that the let's just say that it's at x equals 3. For the vertical asymptote, again, it's a guiding function of the line. So maybe the function does something like this, in which case, again, it continues out forever going in this direction, so there is a horizontal asymptote, but that is not necessarily a discontinuity. And then maybe it does something like this in the other section. But again, in at least one direction, the graph must approach either positive infinity or negative infinity. And again, this is how you will define that vertical asymptote. For a hole, on the other hand, you should actually identify what that y value is, and it looks like I filled that in, but I'm going to go ahead and that's a hole right there. I'm going to hole, okay? So we should probably be very clear about where the hole exists at being x equals 0, but the y value being 2. Meaning that this point on the graph doesn't actually exist on that graph. Very much like that of the vertical asymptote. Again, that line doesn't actually exist on that graph. That graph is just guided by that line. That hole is just a placeholder for a point that should be there, but isn't really there. So, with all these three different types of discontinuities defined, how would we identify these types of discontinuities on an equation? So, not looking at a graph, but if we're given a function and asked, well, what's the discontinuity of that particular function? Let's start with f of x equals to x squared minus 25 over x minus 5. This particular function, if you're trying to identify the discontinuities, your first step is to identify the domain. In the previous video, we identified the domain of this function to be x is not equal to 5. With that being identified, all we have to do is identify or clearly pigeonhole this discontinuity, because that's what the domain issue is. When it's a single point of a domain that doesn't exist, that single point will generally either be a jump, a hole, or a vertical asymptote. In this case, to identify which one it is, we're going to take that original function f of x, we're going to factor everything in the numerator and everything in the denominator. So x minus 5, x plus 5 on the top, and we're going to have x minus 5 on the bottom. You're going to notice that an x minus 5 on top can algebraically cancel out with an x minus 5 on the bottom, and that discontinuity will be eliminated. Or theoretically, I don't know, left in terms of a hole there. That thing that was there is now gone. When it's gone, again, that creates a hole. So if I were to try and define the discontinuity, again, I would say that a discontinuity on this function is x equals to 5. and then I would have to label it either as a whole or a vertical asymptote. And again, this is how I'm going to abbreviate vertical asymptote. And because the factor that created that discontinuity canceled out, that factor creates that discontinuity becomes a whole in that problem. So again, in this case, I wouldn't have any vertical asymptotes because every discontinuity is either a whole or a vertical asymptote. It's never both. And since we only have one discontinuity, we can only have either a whole or a vertical asymptote. The next function, g of x, that we looked at in the previous video was x over x squared minus 25. Now, it's important to note that the domain of this function g was x cannot be equal to plus or minus 5, which should imply that the discontinuities, I'm going to abbreviate discontinuities with dis, are x equals to plus 5 and x equals to minus 5. Now, you can write that the same way as I wrote it up here with the plus or minus 5, but the reason why I wrote it as two separate values is because it is possible for each of those values to go into different locations. So it's possible for this x plus 5 to end up being a whole, while this x minus 5 ends up being a vertical asymptote. It is also possible that they both go into a whole. It's possible that they both go into the vertical asymptote. It's a matter of what the algebra shows the function to do, and then the algebra is going to tell me which one it is. Now, I'm going to do the same thing I did with the previous example. I'm going to factor everything in this problem. So on top I have x, on the bottom I have x minus 5, and I have x plus 5. Now you got to notice that here that there's no x minus 5 on top. Sure, there's an x, but not an x minus 5 as a factor. Same goes for the x plus 5. So with the fact that x minus 5 and x plus 5 cannot cancel out with anything on top, they can't create the whole like in the previous example. Again, these factors canceled out. The factor that created the discontinuity became a whole. These factors can't cancel out, and those factors that create those discontinuities are then going to become vertical asymptotes. So this particular function has two vertical asymptotes, two vertical lines that guide the function and how it behaves. The last function we looked at was h of x is equal to x plus 5 over x squared plus 25. And it's important to note that this particular function didn't have any domain issues. And therefore, if it doesn't have any domain issues, it has no discontinuities. If it has no discontinuities, then there can't be any locations where it's going to create a whole, and there aren't going to be any locations where there's going to be a vertical asymptote. So again, I'm going to write NA for a couple of these. NA is acceptable, none is generally acceptable. But these are the ways that you're going to define wholes and vertical asymptotes graphically, and how you're going to be able to algebraically identify them via a function.